Good afternoon to all of you. I am Dr. Arvind Kumar Singh from UR Rao Satellite Center, Bangalore, India, and I am going to present the paper with the title Hyperspectral Band Selection based on Spectra Division and Deep Convolutional Neural Network, and the paper ID is 167. The co-authors of the paper are Mr. Renu Venkateswamy Sunkara from UR Rao Satellite Center, Bangalore, India, and Dr. Govind R. Kadambi from MS Ramaiah University of Applied Sciences. Content of this paper consists of presentation on abstract introduction, literature survey, problem definition, proposed work, methodology and implementation, results and discussion, conclusion and inferences. In abstract, here we present a Ripper method based on spectra division and deep convolutional network neural network. We show the simulation results of the proposed method on two challenging hyperspectral datasets such as Pavia University and Indian Pines. In addition, we also present the comparison between the representative Ripper methods like SVM Ripper, KNN Ripper, RF Ripper and DDCNN Ripper and the proposed SDCNN method. For comparison, the popular classification metrics such as overall accuracy, average accuracy and kappa coefficient are used. In introduction, we know that the hyperspectral images have a large number of contiguous spectral bands, have high spectral resolution, which means that there is rich spectral information and have low spatial resolution. However, the hyperspectral images pose problems or challenges such as data redundancy and high dimensionality. To address these issues, there are three band selection approaches such as filter, Ripper and embedded. Among these, the estimated accuracy of the classifier in Ripper based band selection approach is the best available heuristic for measuring the degree of appropriateness of the selected bands. However, traditionally for hyperspectral image band selection using Ripper methods, the selection of initial band set is arbitrary or random, and more importantly, the evaluation criteria for the selection of band is always based on overall accuracy, which leads to the issue of non-consideration of class imbalance. Hence, we have been motivated by the fact that there is a scope for improvement in the band selection of hyperspectral images by addressing both the issues. In a literature survey, we see that Ku et al. 2014 presented an SVM based band selection by kernel parameter optimization. However, this method has the complexity in the selection of proper kernel for a given dataset. The Pune et al. 2016 presented an RF based hybrid based band selection approach for hyperspectral images. This method suffers from the computational overhead and high training error. Zhang et al. 2017 proposed the band selection of hyperspectral images using deep convolutional neural network and distance density, which involves random partitioning of bands. Pal, Charan and Priya 2021 proposed a KNN based band selection of hyperspectral images. This method uses only overall accuracy band evaluation criteria. However, the heuristic HSI band set obtained using SVM, KNN and RF Ripper suffers from random initial band set selection, whereas DDCNN Ripper suffers from random partition of spectral bands. Coming to the problem definition, given the hyperspectral image of dimension m cross n cross z, where m, n and z refers to the number of rows, the number of columns, both m and n represent the spatial dimension, and the spectral bands, the spectral dimension. How to obtain the resultant hyperspectral image of dimension m cross n cross d such that d is less than z, where d refers to a smaller number of reliable and suitable subsets of spectral bands through spectra division, while addressing the initial random based set problem prevalent in Ripper based band selection. In the proposed work, this figure, that is figure number 1, shows the proposed SDCNN for hyperspectral image band selection. Here SD means spectral division. The entire band of original hyperspectral images are divided into three groups such as visible, near infrared and shortwave infrared. With the help of spectral division, now a wrapper method with 1D CNN as the base classifier is supplied with the training data, and one of these groups as initial band set instead of the traditionally used random band set, and the performance of the classifier is evaluated. The suitability of any additional band to this group of bands is evaluated group based on the criteria. If the criteria is satisfied, the band is added, otherwise it is discarded. This process is repeated for each group of bands, and the best band set among them is selected as the final band set of the SDCNN method. The classification of the entire hyperspectral image is performed using 1D CNN with the final band set obtained from the proposed SDCNN method, and we get a classification map. In the methodology and implementation, we take the given hyperspectral image. We then perform spectral division on the hyperspectral to get visible NIR and SWIR bands. We execute 1D CNN using training data with visible NIR and SWIR bands as initial band set. Then we compute the decision metric using the confusion matrix obtained from the ground truth labels of validation data and predicted labels. We then add a band to the initial visible NIR or SWIR band set and check if it satisfies the decision criteria. If yes, then add the band to the resultant candidate band set, else discard the band. Continue till the last band and then select the best band set among the resultant band set with visible NIR SWIR as initial band set. After the classification map is obtained for each candidate band set, the confusion matrix is obtained as shown below. More specifically, confusion matrix with validation data labels and predicted labels for each candidate band set. A matrix is shown in the confusion matrix, which is A. Evaluation metric of each candidate band set is shown in the second expression, which is the evaluation metric. This expression gives the average of Y and AA. Decision criteria to add the band. In decision criteria, we check if the present is better than the best value so far. For all the simulations of the proposed method, the challenging dataset as shown in table 1, such as Pavia University with size of 610 cross 340 cross 103 collected by Ross's sensors, Indian Pines size 145 cross 200 acquired by Everest sensors are used. The Pavia University dataset has 9 classes with the total number of labeled pixels to be 43,923. Similarly, the Indian Pines dataset consists of 16 classes with a total of 10,249 labels pixels. The colors coding for the classes of the datasets also can be seen in the table, that is table number 1. For results and discussion, we show in this table number 2, wavelength range and the corresponding group of bands for visible, NIR and SWIR regions for Pavia University and Indian Pines datasets. For Pavia University, we have only visible and NIR bands. The visible bands are from 1 to 64 and NIR bands from 65 to 103. For Indian Pines dataset, here we have bands from all three groups, that is visible bands from 1 to 32, NIR bands from 33 to 99 and SWIR bands from 100 to 200. Results in discussion continues. Here we show in this table, that is table number 3, the architecture of 1D CNN for both data sets. The architecture of Pavia University dataset has 9 layers and that of the Indian Pines dataset contains 13 layers here. I denotes input layer, C denotes convolutional layer, S denotes pooling layer, F denotes classification layer, and O denotes the output layer. Here in table 4, we can see that the simulations carried out on the Pavia University dataset using the classifier representative wrapper and the proposed method have been presented. The performance of the method has been measured in terms of widely used metrics in percentage, such as overall accuracy, in short OA, average accuracy, in short AA, and kappa coefficient, the K representation. The obtained bands for each of the method has been presented along with the execution time in seconds also. Particularly when compared to the state of the art DDCNN, the OA, AA and kappa of SDCNN are 2.61%, 9.11%, 3.39% higher than those of the DDCNN. In overall sense, there has been an improvement of at least 1.05% in OA and 2.74% in AA and 1.46% in kappa of the proposed SDCNN method when compared to all other methods in the table 4 for the Pavia University dataset. Here in table 5, we can see that the simulation carried out on the Indian Pines dataset, particularly when compared to the state of the art DDCNN, the OA, AA and kappa of SDCNN are 8.13%, 6.75% and 9.32% higher than those of the DDCNN. In overall sense, there has been an improvement of at least 5.35% in OA and 3.98% in AA and 6.19% in kappa of the proposed SDCNN method when compared to all other methods in table 5th of the Indian Pines datasets. For the Pavia University dataset, the classification maps obtained using the reference classifiers such as SVM and representative wrapper methods such as SVM wrapper, KNN wrapper, RF wrapper and DDCNN wrapper, and the proposed method along with the ground truth and RGB images are shown in this figure, that is figure number 2. The classification map in the H is the best among the presented classification. Similarly, for the Indian Pines dataset, the classification map in figure 3, H is the best among the classification maps which proposed. From figure 4, the total number of bands obtained by the SVM wrapper, KNN wrapper, RF wrapper, DDCNN and SDCNN are 90, 89, 66, 20 and 44 respectively. The least number of bands, that is 20, are associated with DDCNN wrapper and the highest number of bands, 90, are with SVM wrapper. These bands show that the SDCNN is the second best in the terms of the number of obtained bands. However, the SDCNN offers the highest classification accuracy than all of the methods. From figure 4b, the total number of bands obtained by the SVM wrapper, KNN wrapper, RF wrapper, DDCNN wrapper and SDCNN are 115, 84, 50, 20 and 117 respectively. The least number of bands, that is 20, are associated with DDCNN wrapper and the highest number of bands, that is 117, are with the SDCNN. These bands show that the SDCNN has the highest number of bands in terms of the total number of obtained bands. However, the SDCNN offers the highest classification accuracy than all the methods. In conclusion, the proposed SDCNN method addressed the random initial band set problem so far prevalent in wrapper based band selection of hyperspectral images and demonstrated the superiority in terms of classification accuracy over the representative spectral wrapper methods like SVM wrapper, KNN wrapper, RF wrapper and state of the art deep learning based spectral classifiers such as DDCNN, and also obtained the best resultant band set for challenging datasets such as Pavia University and Indian Pines. We can conclude that before this paper, there are limited attempts to address the random initial band set selection in wrapper based band selection method, whereas with this paper offers a reliable resultant based band set for each dataset while addressing the random initial band set problem through spectra division of the bands for wrapper based band selection. There are some references in the proposed method. So thank you very much.